In this presentation, I would like to discuss the topic we work on, which is anomaly detection in wireless sensor networks. Wireless sensor networks became widespread, supporting various tasks such as traffic lights control systems or environmental hazard detection. They may also be part of critical infrastructure and perform health monitoring. From a safety point of view, anomaly detection suitable for wireless sensor network is key to ensure seamless operation and early threat containment. However, wireless sensor network systems are hard to monitor due to ubiquitous deployment, devices with constrained resources, and diverse ecosystems with devices from many vendors. Because of all these reasons, the research is focused on anomaly detection suitable for wireless sensor networks. Key aspects for the research are limited computational power, inability to capture all threats, resulting in class imbalance in datasets, and attackers becoming more sophisticated to hide malicious activity in normal traffic. All these lead to challenges to create a model suitable for wireless sensor networks that can address future threats, create fingerprints of normal behavioral patterns, and define criteria for anomaly. For demonstration and datasets acquisition, a simulated environment was used. An example of deployed sensors is presented on this slide. Wireless sensor network is connected with the Internet via the Edge interconnecting router. The sensors try to reflect typical deployment where measurements are pushed to the network or devices are controlled remotely. Anomaly detection based on graph comparison is researched as a promising way to capture topology and data patterns anomaly. Machine learning is used for classification with one-class classifier to enable detection of unknown threats. The detection can be implemented at the edge to cope with geographical distribution of sensors. It also prevents tampering as there is no need for deployed probes. Broadly speaking, anomaly detection requires definition of entities and parameters to monitor, acquisition of normal and abnormal samples, supervision with anomaly measurement, and criteria when to declare anomaly. For demonstration, three scenarios were simulated: normal behavior, malicious topology change, and data pattern change, with exemplary results presented on next slides. On this slide, normal patterns are presented, which are represented in vectorized form. The figure on the left represents normal topology patterns, and the figure on the right normal data patterns. Topology attacks led to change, which is indicated by circles on this slide. Whereas data pattern change is marked by circles on the slide, The magnitude of change is reflected by the distance between points in the circles. Thank you for listening.
Thank you very much, Robert. Any questions from the floor, please use the Q&A panel. Meanwhile, I have a question, Robert. This is about anomaly detection. I would like to hear your thoughts in terms of whether an approach like this would be successful at differentiating between malicious change versus change for normal reasons.
This is a multi-dimensional problem. One aspect of differentiation is to take into account a time domain that hasn't been done here, and also we have something which is called concept drift that is caused changing of our normal fingerprint over time. Now this is quite interesting question, because if there is a concept drift which is legitimate, then it would detect a change, but it's difficult to say whether it is normal or abnormal. However, because I'm taking here a geographic kind of distribution, paths taken by data, I could detect the change if the path is changed. So it depends how the change is implemented. So this is a very valid question that, concept drift is very difficult to distinguish, but an attacker would need to be very sophisticated in order to mimic, paths. And also in the future, I would like to talk about the time domain as well. So it's very difficult to come with malicious pattern that would match fingerprint that I'm trying to acquire.
Okay, thank you, Robert. There are a couple of questions on the Q&A. Thank you. I'll go for the first one as it appeared. A question by Christopher Christie. If sensors gathering and transmitting real-time data are a fundamental requirement of IoT systems, the security of that data is critical. Do you have a recommendation about the leading technology to do this, Robert? Any quick thoughts on that?
So that's for security of data that's passed by sensors, yes? Actually, typical way to protect this is by encryption, and this is end-to-end encryption that is implemented, between sensors and end systems. Now, the problem is we are talking about security of physical systems. If this is out there, this is running on constrained devices, then the security can be circumvented, keys could be recovered, and ultimately encryption broken. This is a problem, because for sophisticated attacker and who has access to devices in the field, actually he can get the information really easily and decrypt the traffic. So to answer this question, it is an issue. The method that here it doesn't require knowledge about data, so it respects privacy. It gathers some sort of statistics, but in general sense, and security, end-to-end security of traffic generated by sensors, this is an issue.
Okay, thank you, Robert. There is one more question by David Butler from the BBC. In the interest of time, David, if that's okay, I'm going to ask Annette and Becky to put you and Robert in touch offline. Because we need to move on to the next talk. Thank you very much, Robert.
Thank you.